So we were discussing bivariate normal and random variables, and we'd understand how the joint density looks like. So in the middle of proving this theorem, when you have a bivariate normal random variable, how do you show that density exists, right? So then, of course, we've done some pictures of density like before, but we had come to this key step. We said that if you assume this key step, then we know how to show that joint density looked like the one that we had. So the way we did this was, we said that assuming this key step, that we're able to show that there are two independent normal random variables with such that the probability of y1 less than or equal to a and y2 less than or equal to b is given by this probability on this side, where star 1, star 2 and star 3 are on this side. We're able to show that probability of y1 less than or equal to a and y2 less than or equal to b came out to be the correct form that we had discussed before. That is exactly the same as the one that we had. So once we know that, then this immediately will imply that G is the PDF of y1 and y2. So all you're left to do is to show claim 1 and the key step. So how does one show that? So let me try and do the proof of key step. So let's write down the proof of key step. So here what you do is, you don't go to Z1, Z2 directly. You have an intermediate step in which you work with. So what I'll do now is, I will let's say let Z1 and Z2 be two independent normal 0, 1 random variables. Very good. So once I have this, I have two independent normal variables. I will define my two new ones called u and v. So I'll take u to be equal to sigma 1 z1 plus mu 1 and v to be equal to, so be a little complicated, so sigma 2 times mu z1 plus square root of 1 minus rho squared z2 plus mu 2. So these are two definitions of u and v that we will use. And we use random variables u and v to compare the probability of y1 less than or equal to a and y2 less than or equal to b. So the first thing to observe is the following. You look at, let alpha and beta be elements of R. Okay. Then let's look at alpha times u plus beta times b. So what's that going to be? That's going to be equal to, so if you look at the above, so it's alpha times sigma 1 times z1, and there's another one coming from the v term, so I'll call that as beta times sigma 2 times, so this is a rho, I don't want a mu here, I want a rho here, sorry, sigma 2 times rho. Plus, what is Z2 now? Z2 will be beta times sigma 2 times square root of 1 minus rho squared, the whole thing times Z2. And I'll have plus some constant terms. I'll have alpha times mu 1 plus beta times mu 2. This is what alpha mu plus beta v looks like, right? So alpha u plus beta v looks like this person right here plus this times z2 plus this constant term. Now if you notice, Z1 and Z2 are both normal random variables with and independent, right? So here we'll go back and observe some facts about linear combinations of independent normal random variables. So notice that this has one independent random variable, normal random variable, another one, and it's a linear combination of all of them, right? So and you're adding a constant. So it's an easy exercise to sort of verify from our previous work that since this is a linear combination, I'll make this into orange, of Z1 and Z2 and plus a constant, and since Z1 and Z2 are normal random variables and independent, Z1 is independent of Z2 and Zi are normal 0, 1 random variables, we have alpha u plus beta v will be distributed as normal with what mean will it have with normal? It's a linear combination of independent normals. So the mean of Z1 and Z2 are 0, that's right here, but you're adding a constant. So this is what the mean of the new random variable will be. So normal mean of this, let me remove this bracket here. So it's normal, okay, it's normal with this mean, right? This mean. And what's the variance going to be? The variance will be the square of the other two terms, right? So the variance will be square of this plus square of this, right? So I'll copy that down here. I'll paste it. I'll make it a little smaller so you can see it a little better. Okay, I'll make it a little smaller. I'll put a small one here. So plus squared plus this squared. So that's what the normal is going to be, right? Because I'm just if I'm scaling a normal random variable, its variance will just be multiplied by the whole square of that. So that's the distribution of alpha u plus beta v. So what I do, I start off with u and v like this, and alpha u plus beta v is normal with this parameter mean and this parameter as variance. This is what we do first. But now you observe, therefore, alpha u plus, since alpha and beta were arbitrary, that is, there any two real numbers, and we had shown that for any two real numbers, alpha u plus beta v is normal random variable. This implies that u and v is bivariate normal. Is a bivariate normal random variable, because any linear combination of u and v is a normal random variable. So by definition, this is normal random variable. Now again, you do another calculation. You look at how u looks like. U looks like sigma 1v plus sigma 1z plus mu 1, right? So it means we can compute the mean of u and the mean of v, right, by this calculation idea. And you can compute the variance of u plus variance of v, right? You can do both by looking at the expression for this. So let me just try and see if I can cut and paste that for you and show it to you the answer. So let me go here. You observe that u1 looks like this and v looks like this. So from these two things, you can just do a simple computation and show that the mean of u will be just same as mu1. The mean of v will be same as u2, and the variance of u and variance of v is, so this is a little bit mistake here. Let me just copy it, make it correct. So let me just call this a little bit. Let me just So mean of mu2 is E of V, mu1 is E of 1, E of U, sorry, and the variance of U is sigma 1 square. Right? And the variance of V, you have to do a little bit further computation to get these two numbers here. This number of variance of V, and the covariance of UV is this. Now we already know that if you just observe carefully, this guy is the same, this person right here is the same as E of y1, that is the same mean, right? This person right here is the same as E of y2, and this person is the same as variance of y1. This person right here, after all this calculation, is the variance of y2. This person right here is the same as the covariance of y1 and y2. You already saw before, if the mean and the covariance match and the variance match, then the distributions are the same for the two bivariate normals. So therefore, from that theorem, we know that y1 and y2 have the same distribution as u and v, because their means and covariance matches. This we did last time in the previous week, that if you have two bivariate normals, if they have the same means, the same variance, the same covariance, then they have the same distribution. So it means probability of all the probabilities of y1 and y2 are the same as v1 and v2. That's the key claim here, right? I mean, we know that probability that y1 is less than equal to a and y2 is less than equal to b is the same as the probability that u is less than equal to a and v less than equal to b. So this implies for all a, b, and r, this is true. So this is a very nice fact we have. Now what is u and v? Let's go grab u and v. What is u and v? U is defined as this clever way, right? Let me grab u and v so that we can just keep it in mind. So let's copy it here. So here I have, let me put this is the same as this. Let me mark these guys in orange so that I know that I'm changing the u and v differently, right? So the above probability, if I erase these things after I understand this, is the same as the above probability is equal to the probability of this person is less than equal to a and this person is less than equal to b. This is what I have, right? And if you just follow the calculation properly, you will just get that this is the same as the probability that z1 is less than equal to a minus mu1 by sigma 1 and z2 is less than equal to what we had before, that is b minus mu2 by sigma 2 times by sigma 2 times rho 1 minus rho squared plus the other factor, that is the plus or minus, let's say I put minus now, minus rho times z1 by rho 1 minus rho squared, right? This is what we have. So let me move this across this way so I have space for this guy. I put this guy right here, which is what I wanted to show in claim 1, right? In claim 1, that means I have the same as saying probability that z1 is less than equal to star 1, z2 is less than equal to star 2 minus star 3 times z1 is what I had, and star 1 is equal to a minus mu1 by sigma 1, star 2 is equal to b minus mu2 by sigma 2 times 1 minus rho squared, and star 3 is rho minus rho by 1 rho squared. And that's what the key step was. So let me just recap a little bit. Open a new window. Let me go back here. Again, so the key trick in this whole calculation of this key step was defining this new random variables u and v. Because once I defined that, then it's just linear algebra. I just have to just look at alpha u plus beta v. They were linear combinations of z1 and z2 plus a constant. That means they were normal distributed, which means that if you have any alpha and beta, alpha u plus beta v is normally distributed, which means that uv is a bivariate normal random variable. And then once we had that, then we found out that the mean of u and the mean of v same as y1 and y2, so were the variances and the covariances. That means that they both had the same distribution, which means that for every a, b in R, probability of y1 less than or equal to a and y2 less than or equal to b is the same as u less than or equal to a and v less than or equal to b. And once you have that, all you have to do is finish off the computation this side. You just get the fact that probability z1 less than or equal to a minus mu1 and z2 less than or equal to this, which is the same as this expression right here. So let me mark this in orange so that it's the same thing as before. And let me make this black as white. And which is exactly what the claim was, right? Let's just go back to the claim. What is the key step? The key step was to show this, which is what exactly we have shown. For any a, b in R, we have shown that probability of y1 less than or equal to a and y2 less than or equal to b is the same as z1 less than or equal to star and z2 less than or equal to star 2 minus star 3, where star 1, star 2, star 3 are given by this expression. Very cool. And this should be a plus star 3. I'm sorry, I just made a mistake. Star plus rho. So let me just do this a little bit. This is the minus naught. Very cool. So the proof is complete. So I've shown you the proof that the bivariate normal random variable has a joint density given by exactly what we have here, right? By the expression right here. Very nice. This is a very nice hard theorem to show, and we have shown that theorem. So now if you want to work with bivariate normal random variables, you can use this density function to compute probabilities and various things.